creative solutions.
Okay, yeah, thank you. Well, actually, my talk overlaps and in many ways and with Peter Parfit's, Professor Peter Parfit's talk this morning. And but I just start continuing my discussion of yesterday. So yesterday I derived the diffusion equation, the equation that describes the time evolution of the distribution of the rod-like particles in shear flow, and how we can derive the equations and how we can derive the expression for the stress tensor. Now, so that is essentially for the dilute solution. Now, today I start my discussion with how to generalize that argument to concentrated solutions where the particles interact with each other. Concentrated solutions, I mean two situations. There are two situations, as it has been talked by many people. If the concentration is low enough, we have this situation where the rod-like polymers distribute isotropically. We have an isotropic concentrated solutions. And if we increase the concentration further above certain critical concentration, we have this liquid crystalline state. And I will discuss the dynamics in both situations. Now, first, let me talk about the isotropic solution. I just want to emphasize this point. So the dynamics we need to deal with, this is a situation that we need to deal with, where the many rods are entangled. They are hindering each other. The rotational motion are hindered by other rods. And so one can expect that the rotational diffusion, rotational Brownian motion of this situation is essentially determined by the viscosity of the surrounding fluid, the viscosity of the solvent. But in this situation, since rotational motions are hindered by other rods, we expect that effective rotational diffusion constant in this situation must be much less than that in the dilute solutions. And I want to first discuss how much it should be small, how much smaller of the rotational in the rotational diffusion constant. Well, the rotational diffusion constant in this situation is essentially determined by the rotational friction constant. That is the friction constant is the relationship between the torque exerted by the surrounding fluid when this rod is rotating with an angular velocity omega, and it is essentially given by the viscosity of the surrounding fluid times the length cube. L cube of this rod. Now, in this situation, an estimation and an argument to estimate the rotational diffusion constant in this situation is the following: that since essentially this is the sort of called tube models, as long as this mutual configuration of the rods are not changed, the rod can't change. So its orientation is essentially confined in this tube-like region, in the regions restricted by the other rods. So for the rod to rotate, either this rod has to escape from this constrained region, or either one of the rod has to one of the rod moves in this way and remove the constraint. The one argument is that, for example, that this is a way of this is a mechanism for the rod to rotate. So the rod moves in this way. If this length is L, and if the A is the diameter of the tube, if the rod moves along itself, the distance L, it can escape from the original tube, and it can rotate slightly. The angle that it can make is essentially determined by A over L, where A is a typical diameter of the tube. And one can show that this A from this is purely assuming that these rods are distributed randomly. This is a simple problem of probability. A is given by this expression. N is the number density of the rod. So the delta theta is given by this, and the time needed for the rod to diffuse to the, by the distance L is essentially L square divided by the translational diffusion constant of the rod in a tube. Okay, so it is where dt naught is a translational diffusion constant along the tube. And the rotational diffusion constant is essentially given by the delta c square divided by this time tau. And that ends up, and this argument ends up that effective diffusion constant is smaller than that in the dilute solution by this factor NL cube minus 2, but to the power minus 2. Since in a concentrated solution NL cube is much larger than 1, so the rotational diffusion this indicates how small the rotational diffusion constant is in a concentrated situation. You can regard this the smallness of the rotational diffusion constant saying that the effectively the rotational diffusion constant in a concentrated solution has increased dramatically. Effective rotational friction constant increased by this factor NL cube, this square. That is for the rod to rotate, it has to travel. It has to make a long traverse. Okay, it can't rotate directly. It can rotate by traveling a long way by repeating this process. All right. So now in that situation, if you look at the expression for the shear stress tensor, shear stress in the shear flow, this is the expression for the stress tensor in the solution of rod-like polymers, and it's given by this orientational part plus this the extra energy dissipation part, that is energy dissipation part plus the solvent viscosity term. But if we plug in this UX UI, this orientational part is now is essentially is given by gamma dot divided by the rotational diffusion constant, and this now has this dr is now much less than that in a dilute solution, and therefore this term is the dominant terms. And in the end you can show that the stress tensor in a concentrated solution is essentially determined by this orientational order parameter of the rod itself. So if you shear it, you can imagine that the viscosity in this situation must be large because the rod. Okay, so in this situation, the viscosity is very large, but the shearing stress you measure, you feel is directly related to the orientational order parameter of the rod. So you shear the solution, then you orient the polymers, and this orientational order parameter is what you measure by the shear stress. All right, so this is the viscoelasticity. This is a summary of the viscoelasticity in isotropic concentrated solution. And so essentially the distribution function obeys this rotational diffusion constant, the rotational diffusion part, and this omega naught is the angular angular velocity imposed by the shear flow was imposed by the velocity gradient, external velocity gradient. If we solve this equation psi, and you can calculate the stress tensor of the system produced by the shearing flow, by the external flow parameters. And that gives you the relationship between the velocity gradient of the imposed, that relates the relationship, that relates the imposed shear rate to the shear stress. So for example, this is the experiment in the isotropic solutions. So the rod are isotropically oriented. So if you start shearing, so the rod gradually are oriented, and so the this is experiment that says so we apply a constant shear rate. We apply a constant shear stress on the top plate, and then the flow starts, and the shear strain increases like this. And at this point, we removed we set the shear stress equal to 0, and therefore the relaxation. Then the rod tends to go back to the isotropic state. So it hits the random motion of the rod just hit the top plate in this way, and that induces this retraction of the top plate. So this is the origin of the elastic behavior of this solution. And of course, that essentially by solving the set of equations, we can predict how the viscosity depends on the shear rate applied to these solutions. Now, so far this is all for the isotropic solutions. That's a viscoelasticity of isotropic solutions. Now I would like to go to the in nematic solutions, the solutions at higher constant above the in a nematic state. So this has been said by many people. I don't have to repeat. So in the isotropic solutions, the rods are isotropically oriented. In a nematic state, these part molecules are oriented, and this orientational behavior is described by. In the isotropic state, rods are oriented randomly, isotropically randomly. And in the nematic state, rods are aligned along certain directions, denoted by a vector n, called the directors. And the order of the liquid in nematic state is described by this order parameter, un square minus 1/3. Okay, this order parameter is 0 in the isotropic state and becomes non-zero in the nematic state. Now the transition behavior, the phase transition from the isotropic to nematic state has been described. I think again Peter talked about this yesterday. There are many theories, and the simplest theory is this Meyer-Zaup theory, and it says that there is some interaction potentials. Rods, neighboring molecules tend to align in the same directions. So if the one molecule is pointing to the direction u, and the other neighboring molecules is pointing to the direction of u prime, there is an interaction energy that forces them to align in the same directions. And and in the simplest form, it can be described by this potential term u dot u prime square. And therefore, that this term stands for the interaction energy term. and that term stands for the entropic term. And so this is the expression of the total free energy expressed as a functional of the orientational distribution function psi. And this equilibrium state is determined by this condition that this A is minimized, and that gives you this expression, or the at equilibrium psi u satisfies this so this is a nonlinear equation for psi, and it can be written in this form where the distribution, orientational distribution, is essentially given by the Boltzmann distribution in the mean field, and WMF stands for the mean field, the field created by the surrounding molecules to the rod we are focusing on. So this expression can be solved exactly, and the solution looks like it involves this parameter u, or the temperature T, and as we change the temperature, so this is above a certain temperature, this solution has only one solution, that the order x is 0 isotropic state. And if this interaction becomes strong, or if the temperature becomes small, this energy term dominates, and then the rod orients in certain directions. And the solution, but of course that the solution here, you have an n can be in any directors. So this, of course, that in the isotropic state, nematic solutions can orient to any directions. N is a parameter at hand. You can choose n. You can choose freely. So now using the argument that I used, that it's quite easy to extend this equilibrium theory to the dynamics. Now we say that we know the expression for the free energy. Okay, so now just the non-equilibrium state of the rod is described by this distribution function psi ut, describes the set of parameters, the parameters that specify the non-equilibrium state. And given this and the parameters, the free energy is expressed in this way, the same as the Mayer-Zhao type argument. And when the psi changes, so the energy dissipation is written in this form, where theta r is a rotational, the distribution function changes when the rod rotates, and when it rotates, when it rotates, this is energy dissipation function that is proportional to the square of the angular velocity, and this theta r is effective rotational diffusion constant that I described in the previous slide. This is an effective diffusion constant, and so it must be much smaller than the effective friction constant that is much larger than that in dilute solutions. It essentially accounts for the interaction between the rod, the striking hindrance effect between the rod. Well, then if I go through the formalism, I can show that this angular velocity omega is given by this expression. So it is essentially determined by the effective, now rod field, the rotational potential plus this mean field potential. And this is the equation. Do I have okay. I forgot to put this, omega. I forgot to put this omega naught. So in the presence of the shear flow, I have some extra omega. If there is a shear flow, this term has to be omega minus omega 0 squares. And then, okay, in that case, we have an extra term omega naught. And in the end, you will have a time evolution equation for the distribution function in some external shear flow. Okay, the rotational diffusion constant term plus the mean field potential term. And of course, if there is no external field, if omega naught is 0, and if the system is at equilibrium, this is the solution, and that is the equilibrium solution given by the Mayer-Zaupe theory. So this is a very natural extension of the Mayer-Zaupe theory to the dynamics. Also, and then given the Lorentzian, it's easy to derive an expression for the stress tensors, and just take a partial derivative of the Lorentzian with respect to the velocity gradient tensor, with respect to kappa, velocity gradient tensor kappa, and then you have this expression for the stress tensor. So this essentially describes this equation describes the time evolution of the rotational distribution function, and if you solve this equation, you can calculate the stress exhibited by the solution. And at equilibrium, of course, at this stress tensor becomes isotropic. Because in isotropic solution. Now, so to proceed further, we restrict ourselves. So that this equation, this equation can describe the viscoelasticity, and also it can describe the nonlinear response, nonlinear viscosity. But we will restrict ourselves to let us restrict to the regime where the perturbation from the equilibrium state is small. The linear viscoelasticity regime, the so-called linear regime. Now, the analysis is easy in an isotropic state. So this is an time evolution equation in the isotropic state. I forgot to mention that, of course, that if the interaction effect is non-negligible, we can have this, and we can include this term in the distribution function, and the equilibrium state, the equilibrium solution of this equation is has both isotropic solution and the nematic solutions. And below, if the concentration is low enough, the equilibrium solution, this equation has an equilibrium solution where the system is isotropic. So if in the linear regime we can solve this equation using the perturbation theory. So we assume that the psi naught plus psi naught is an isotropic state, so it's given by this isotropic distribution functions. So we can linearize this equation, and we can solve these equations using this standard perturbation theory psi 1. And essentially, you can calculate the viscosity in the isotropic solutions. Let's see. Right. Now, we can do the same sort of analysis for the nematic state, but here you have one complication. The one complication is that nematic state, if you want to do the same kind of the perturbation analysis, we have a problem. We have I don't know, maybe this is an well-known, there must be some mathematical wording for this, but the thing is that in the nematic state, the equilibrium solution is not unique. There are many. It involves an extra parameter n. It is a free parameter that is at hand. So if there is no velocity gradient, we have these equilibrium solutions. But if we apply a small external perturbation shear rate, if we apply a small shear rate, then the distribution function is disturbed from the equilibrium state slightly psi1, and so we can of course linearize the equation. But this in doing the linearization, this we do not know the equilibrium solution. We do not know which n is. So you have to determine both the psi1, the perturbation from the equilibrium state, but we also have to determine the equilibrium state. What is the reference equilibrium state? And so this is a complete. There must be some name, but this is some mathematical problem. But anyway, so that we can. Okay, there are. But that type of the mathematical problem can be handled, and when I can go to that expression, but I skip that part because I mean this is for this audience, I think that's not the very attractive part of the problem. I mean I want to discuss the relationship between this theory with the Leslie-Erikson theories in the nematics. In the Leslie-Erikson theories, so they use that the state in the liquid crystalline state is described only one slow variables, directors, and by using that by completing this analysis, you can derive actually the Erikson-Leslie's constitutive equations. But there is an other alternative, but this has also been taken by people like by the many other previous workers. So in the Leslie-Erikson theory, the theory can be derived using the Onsager's principle. We say that the state of the liquid crystal is described just by one parameter n, the director, and so the free energy of the system is independent of n. And the dissipation, so therefore the Eulerian is equal to the energy dissipation functions, and energy dissipation function is written as in a quadratic form in terms of the n dot, the directed change, and the velocity gradient tensor kappa. And given this Eulerian, the time evolution equation for n dot is described is determined by this equation. That you can call it Onsager's principle, but maybe call it Lagrangian dynamics. And also that this stress tensor can be derived by this formula. Leslie-Erikson theory. So we can derive by this procedure. You can derive a time evolution equation for the n and this expression for the stress tensor. That part becomes a bit involved. You can derive the expression for the energy dissipation function purely as Erikson and Leslie did by a purely symmetrical argument. So it has to be a quadratic form in terms of the n dot and the velocity gradient kappa, and also it has to satisfy some rotational invariance. So if you rotate the whole system with a constant angular velocity, the energy dissipation should not change. And with that requirement, you can show that the energy dissipation function is written in this form. Epsilon dot is the symmetric part of the velocity gradient, the time derivative of the strain tensor, and n dot tilde is given by this expression. So this is an expression for the energy dissipation function, and defy the n dot. Okay. Okay, I have not written down the whole expression, but the defy the n dot is by setting defy the n dot is equal to 0 gives you a time evolution equation for the equation for n dot, and this expression for the stress tensor is derived by taking a time derivative by taking a partial derivative of phi with respect to the velocity gradient tensor. Now, this is, I have been discussing about the what's happening for the homogeneous state, where the everything the things do not depend on positions, but in generally this director is a function of the position, and so we need to describe the well, this is the Ericsson-Leslie theory, the nematic hydrodynamics, and so the state variables essentially nRT is the state variables, and okay, and so we need to if the director is not constant, we have an elastic energy, the Frank elastic energy term, and this now plays the role of the elastic free energy of the system, and A dot can be calculated by this formula. So the A dot is changes, so if n changes if n changes in time, so this is a direct contribution of the change of n, and this, but the A dot also changes because by the convection of the flow, and this, so if there is a velocity, macroscopic velocity v, and this is an expression for A. And so we need, in this case, the n is a director, but the time evolution of n is determined by the it involves the other variables, v, velocity, n dot, and v are the variables that we need to describe the time evolution of the system. And so therefore, this is the expression for the Radian in the inhomogeneous system. Now it involves the energy dissipation function is written. So excuse me. This is n dot is written as a quadratic as a functional of n dot and gradient of v, and A dot is given by this, and this stands for the constraint that the n times n dot is equal to 0. This stands for the constraint of the incompressibility. And by just minimizing this Rayleigh form with respect to n dot and v, you have the set of equations that is written as that is called the Ericsson-Leslie's equations. The full set of equations becomes quite complicated. I am not repeating it here. Now, of course, the other part, I think this was also mentioned in Peter Parfy's lecture this morning. So we can since this time evolution equation can describe the non-equilibrium and the far from equilibrium solution, people have solved either by the Voronoi tessellation or by just some harmonic expansion, spherical harmonic expansion of this expression. So there are many many phenomena that this just indicates. I think this so this slide shows this is just a result how the orientational directors or the average orientation changes in as you shear the samples. This is a situation of the the solution is such that even in the shear rate is constant. The solution of this equation is not this system. This nonlinear equation for the psi does not have a steady state solutions. It has this time varying solutions, and this is one of such solutions, saying it is called kayaking or wagging and some names. It has some names. And accordingly, that this the relationship between the stress and the shear rate becomes quite unusual. Shear stress is not a monotonically increasing function as is not a monotonically increasing function of the shear rate, and also the normal stress changes sign in a certain first normal stress difference changes sign from positive to negative in a certain shear rate region. So it positive, negative, and positive, and so the system is shows a very complex and stress response to the shear flow in a nematic rod-like polymers, and these behaviors has indeed been observed experimentally. So this theory explains certain aspects of the flow properties, mechanical properties, the viscoelastic properties of the solutions of rod-like polymers. So this is just a conclusion of my talk. So essentially, I only stated one commitment, one message. One message is that the Onsager's principle, or maybe it may be appropriate to call it Lagrangian mechanics. Generalized Lagrangian mechanics may be a more appropriate word, but this is my purpose here was given that the Onsager. Okay, let me keep talking about this Onsager principle. By using the Onsager principle, you can derive the viscoelasticity of rod-like solutions or many other solutions, many other non-equilibrium phenomena taking place in soft matter, diffusion, and rheology, permeation, and so I think this is a quite useful principle. And here today, what I said is that the viscoelasticity of rod-like solutions in both isotropic solutions and in nematic solutions are consistently derived by this Onsager principle, just by adding the extra interaction term, and then just follow the procedure, and that gives you that gives you the characteristic of the viscoelasticity of rod-like solutions. So my message here is that this useful principle called the Onsager principle. As we heard, that it may be called the generalized Lagrangian mechanics. There may be other names. My purpose here was just this is so important, and I think I wanted to have some names to call it. To quote it, Lagrangian mechanics, generalized Lagrangian mechanics is not documented. The certain textbook says that without explaining the limitation and explaining some fundamentals. But I wanted to make it more widely accepted. I think the name does not matter, but I think this is a very important principle and the important and useful principles. Thank you very much for your attention.
Are there any questions?